Okay, so we were discussing the two kinds of modeling a system. One kind of modeling is analytical modeling, right? What is analytical modeling? Using mathematical equations, using algebra, using some already existing equations, like we'll discuss. For example, already know basics of electricity networks. We know Kirchhoff law, Kirchhoff current law, right? All those transformer equations. So all this equation we can use for modeling the analytical model of the transistor or in an equation level. So without needing to really work on the transistor or troubleshoot it, while going the taking down the transistor transformer and putting all those input and testing, it's a very cumbersome, very difficult task, right? So instead of that thing, we can model analytically. What is analytical modeling? Using theoretical equations, already existing models, already existing transformer, or we can make a model. For example, transformer is already studied device or system, so we already have existing models. But if a system is given without, you don't have any model, then you have to model it from scratch using physical laws, using electrical loops, Kirchhoff law, voltage law, etc. Okay, so this is one way, and second way of modeling is experimental modeling. What is experimental modeling? I already discussed. Again, we have to take the transistor down, and experimentally we need to verify what is, if this input, what is out, extra. Okay, so that is very difficult. A lot of effort, human effort, technical effort, and a lot of testing, and it's not practical, right? So this is one example. Maybe, yeah, say this is another example I'm going to give you. Say for example, this is, see, you have seen this kind of thing in exhibitions or in the right, in the entertainment places. So this is, if you are told to understand the is it works properly, because there have been instances where people got accidents, people fall down. This is going, I think this is a pendulum, right? I think you can appreciate this. This is a kind of pendulum, all those for entertainment purposes. But there have been some incidents where uh, this kind of systems had like accidents, like it just go over the overhead, and people fell down from it. So in order to understand whether it works properly or not, you're told to investigate system. No, it is one way is an experimental thing that we already discussed. One thing is you try all those uh, different speed. You make it work in high speed, and you see what whether it is functioning properly. Is the torque proper? Is the how much displacement it is getting? Is it capable of uh, getting into accidents or something like? You just analyze all those things. That is experimental way. So what is analytical way? You model it using your physical equations, like this is nothing but a pendulum. So if you know to model a pendulum, you can easily model this thing. So right now there are two ways. This my point is, one is analytical way of modeling systems, another is experimental way. Here experimental way is also difficult. You have to waste a lot of power, you have a lot of manpower, effort, and a lot of complications, or even accidents. Sometimes accidents also can happen, and it leads a lot of cost, and a lot of life also sometimes. So experimental way is always difficult. That is why we try to model using analytical way. So we write the equations of pendulum, which you already know, theta, torque, and acceleration due to gravity, g, and weight. So all those equations we will see. So this is the advantage of modeling a system analytically. So we will discuss in this thing different types of modeling, and first of all, the need for modeling. Okay. So I think we can take n number of examples. For example, an aeroplane. You have to model it using experimental modeling is also possible, but that is the last way. First, we can model using analytical methods, using mechanical equations, hydraulic equations, and electrical equations, whatever. Right? And this is very true in automobile industry, where after analytical modeling, they have to test using experimental way. They test the vehicle, they hit the vehicle and see what is the injury happening to dummies, the models of human models. They see the force and acceleration and all those things, they measure it, and they verify whether this protection is sufficient so that human beings are not affected or disturbed. Okay. So today we will discuss, basically start with the modeling of systems. We will model mechanical systems, also electrical electronic system, and we'll also see some analogies. Okay. So the first thing, Um, the first thing we'll start with is just some theory. We need to brush up some theory. before we'll start the okay. So let's start. Okay, the first thing what we have discussed till now is, so today we'll be discussing modeling, modeling of systems, modeling of systems. This modeling is not limited to electrical electronic system, only modeling mechanical system, pneumatics, hydraulic systems, modeling of systems. Okay, so what is the definition of modeling? So modeling is nothing but a mathematical representation of a system or plant, right? It's like we can say this is mathematical representation of system or plant. So what is mathematical representation? We already discussed. We have models of equations, Kirchhoff law, voltage law, all those models of mechanical models, whatever. So this is, you can say, elemental representation. Elemental representation. You can say elemental means we are analyzing a system or dividing a system into subunits, small units. Elemental representation or mathematical representation of a system. So this is some resolution problem. Okay, mathematical representation of what? Representation of a system or a plant. System or a plant, right? System or we can say plant in control system terminology, right? So what does it help us? Why we need such a model or elemental representation or mathematical representation? This helps in analyzing, helps us in analyzing systems. Okay, analyzing analyzing. We have just taken example of troubleshooting. You are told to troubleshoot a transformer or told to analyze the accidental probability of a you can say, toroidal, I don't know what it is called. Okay, so you have seen that thing. It was analyzing the behavior or input output input output pattern of a system or plant, of a system or plant. Okay, first is we are representing using elemental method or mathematical model, which helps us to analyze the input and output, and also troubleshoot, also to uh, failure analysis, etc, etc. Okay, so how we need to model this thing is, we need to understand the dynamics of the system. First thing while modeling is we need to understand the dynamics of system. Dynamics, you should know, understand what are the dynamics, what is system made for, right? What are the particular parameter we are interested in? Is it the efficiency or input output losses, or is it the you can say the torque or the weight or the variation in the velocity, whatever. So we have to specify what are the specific region of interest. That means dynamics of the system should be dynamic of system we are interested in, right? Now, not only we need to understand the dynamics of system, what we are basically looking at is the basically we are looking at the evolution of the system variables. Evolution of the system variables. What do you mean by evolution of system variables? Evolution of system variables. For example, there are a lot of system variables. In an example of transformer, we can see the system variables are different voltages in the input, voltage in the output, current at the input, current at the output, and different voltages as within the system. Within the system also there are different components. So what is the voltage at each of these components? This is evolution. And what is the change of voltage at different points? What change of current at different points? If you're talking about mechanical system, what is the velocity at different points of a pendulum? The example which you have taken. Or what is the acceleration? How much a person will experience an acceleration within the system? Okay, so these are the system variables which we are interested in. So whose dynamic? Dynamics means change, sudden change, or the way it is changing. Okay, so we are interested in the dynamics of the system variables, and on not all variables we may be interested in. Very some variables only we will be interested in based on the system and your field of study. Okay, now we'll take some example, say for the same discussion we had some examples. Say last class we had discussed temperature control system, right? We'll take an example of temperature control system. Temperature control system. So in this, what are the dynamic parameters we are interested in? Control system, temperature control system. Just like, just it was just a device which we were discussing last time. It was a mm, yeah, heater, electric heater. That was our with some display. That was our discussion. So in that thing, we are trying to control the room temperature, right? So we are interested in the parameter we are interested is in temperature, right? So we are understanding the dynamics of the variation of temperature. So how the temperature is varying with respect to system or the machine input and output, right? And how fast is the temperature varying? That is very important. How fast, how slow, right? And what is the efficiency? So a lot of parameters. So we are interested to model a temperature control system to understand the dynamics of the system variables. Maybe temperature, maybe the speed at which temperature is varying, rate of speed, how much efficiency the system is getting, and with respect to input and output, right? So we need to represent the control system in a mathematical representation. We need to have the mathematical representation of the temperature control device or system, and we model using elemental systems like small resistance, capacitance, amplifiers, etc. Right. So this helps in analysis or troubleshooting or modeling or even design also. Okay. So another example we can say. So another example can be a car, speed control of a car, speed control system of a car, speed control system of a car. Okay. So here also the dynamic parameters are the speed, the acceleration, the braking capacity. So all the different parameters are there. We'll try to model mathematically so that we understand how it changes, how fast the velocity is changing. There's nothing but acceleration. How fast is the acceleration also changing? So using this model, we can understand all those things. And we'll come to our domain, and come to electronics or electrical domain, can say and how voltage and current is evolving. Okay, evolving. This is nothing but dynamism, right? Evolving. How the voltage and current is changing. That's for input and output. And are we getting the desired output? Are we getting the desired output? Okay. Here also the temperature is the desired output. Here is the speed or the trajectory of the car is the desired output. Okay. So these are things for this is why we go for model to understand the dynamic parameters, how the evolution of the system variables, to understand the analyze the system and predict also. We may use for prediction also. When you have model, so we can predict also. So basically, how you represent a model is just a block diagram. Initially, it's like this. This is what we are doing in the block diagram reduction and all those things. But before modeling a transformer, a pendulum, or a car or a temperature control system, we don't know what is inside, right? So we have to know what are the elemental elements inside the system, and also we should know some physical laws and which we should using we should model these elementals, and we should derive a mathematical representation of the system. It can be anything: car, temperature control system, your transformer, your pendulum. Okay. So okay. So first thing we have to discuss, like, how many types of modeling is there? How many types of modeling is there? So the first step is we have a system or a plan. This is system or plan, right? We discuss in control system language. We need to convert this into a mathematical model, right? That is modeling, right? Mathematical model. And convert this into a mathematical model. How? So before this, how we should know what are the different ways, what are the different types of modeling we can have. Okay, so one of the main important ways which we'll be using is most simplified, which already you learned when you started engineering. That means first year, second year, third year. The first step of modeling is understanding the mathematics of the system. And Whenever a dynamic system is there, how to model a dynamic system? That is to differential equation. So the first and most important type of model. So types of modeling. So types of modeling. Okay, first type of most important type of modeling, which we already familiar with, is differential equation model, mathematical differential equation model. Differential equation modeling. Okay, so it is nothing but writing the differential equation. You might have remember writing in physics also. We write the differential equation of a pendulum or a body moving in a slope, etc., etc. So first, this is first way. So basically, we are writing the time domain representation, right? What we are doing in the differential equation? There's a one parameter moving with respect to other. For example, we can um, say d dv by dt, something rate of change of velocity with respect to time, and we model using some um, say x d square x by dt square plus um, into mass, something like into mass. I'm just giving an example of whatever coming to your mind. It's not so okay. Some equation like this. This is the variation of velocity with respect to variation in double variation or double differential variation of the position plus maybe some constant k or something. Okay, so this is I'm giving an example. This is a differential equation of time domain. Can you see this is time domain representation of a system. Can be any system, pendulum or whatever. Okay, so this is differential equation modeling. So what are the other kinds of modeling? Now, second type of modeling is transfer function modeling. That is another important modeling. So transfer function modeling, transfer function modeling, transfer function modeling. Okay, what is happening in transfer function modeling? So the same differential equation which we have, right? It is in time domain, right? We are drawn the differential equation with respect to time, dv by dt, dx by dt, or so this will convert into frequency domain, right? So in transfer function representation, the time domain is converted into frequency domain. Frequency domain. So how we convert time domain into frequency domain? Time domain into frequency domain. How? Yeah, we need to have a Laplace transform or a Fourier transform or the Z transform. So we need a for here for our purpose we'll be using Laplace transform. Okay, so the time representation can be converted into frequency domain representation using Laplace transform. Then that constitutes the transfer function modeling. So what is transfer function? We have already discussed basic about transfer function. This is output by input, right? Ratio of output by input gives a function or a mathematical representation in terms of S domain or frequency domain. So that is called transfer function. Okay. There is second kind of modeling which we'll be using. And what about the third kind of modeling? So the third modeling is state space modeling. That is sometimes we can say the modern control system way of modeling. Right? State space. State space model. We'll be discussing that state space modeling. State space modeling. Okay, so this is based on modern control theory. We can say we represent a system using state variables, and we see what are the variations of state variables with respect to system input and output, and we make a transfer function using those state variables, right? We'll see some examples of state space modeling, although this kind of modeling is uh, very much used in all the control system, even space technology and all those things. All right. Although classical systems are also used, but this is a bit later. So we should understand that. So this is set of state is a set of variables that describe the system, right? Okay, it may be physical or it may not be physical. In differential equation, everything is physical. You should remember differential equation we write everything is physical using acceleration, velocity, position, right, mass, etc. But in transfer function, although it is just a conversion of differential equation into frequency domain, so it is also physical. But state space variables may or may not be physical, but it is just more of a mathematical metrics method. But it describes the system behavior, right? right? It's describe the system behavior. This state variables must describe the system behavior in conjunction with the input and output. Okay, state-based modeling describe this, have different state variables which describe system behavior. Describe system behavior with respect to your input and output. Okay, input and output. Okay, I'm just writing. You have to write in your note whatever the points. Okay. Okay, so usually we use first order differential equation in state space modeling, but in differential equation it can be second order, third order. But here in state space modeling, uh, we are using first order representation, but the dimension of the matrix or the matrix uh, may increase or decrease. But we are using first order differential equation or first order representation. Okay, so so these are the different, I'll repeat, these are the different types of modeling we'll be using. One, differential equation modeling, transfer function modeling, and state space modeling. Differential equation is time domain, right? Where we write the differential equation of the physical phenomena. And transfer function modeling is in frequency domain. We put the Laplace transform of the differential equation and we convert it into frequency domain. Okay. And what about state space modeling? State space modeling, we describe this system using some variables, state variables, right? So state variables describe the system behavior in conjunction with the system input and output. So all by using all these three different techniques, we can represent the dynamics of the system, as we already discussed. The dynamics of the system can be described how the system, evolution of the input and output, evolution of system parameters within the system, like voltage, current, force, tensor, whatever. Okay. So by these methods, we can represent the element of the system, right, of our system or a plant. Okay, so we are making a mathematical representation. So this is nothing but mathematical model, right? So we have discussed three different type of modeling. Now we'll take some examples. Okay, so we'll take a small example. So for example, we have a small circuit. So we have a small circuit. Say for example, I have a circuit like this. Input, this is my input, and we have connecting a resistance, an inductor, and a capacitor. Okay, so this is my system. For example, this input, this is voltage input V, and I'll get the current I, and this passing through resistance R, inductor L, and capacitance C. Okay, so we need to we know the system. This system might have some behavior or some input and output characteristics, but we are interested in modeling the system. Right now, we are given everything. We are given what is the system consists of resistance, inductor, capacitance, and a voltage source also. And we know the system parameter. What are some parameters of system like current at different points and voltage at different points in the system? VL, VC, right? So the different voltage at different points. This is V input, V in. Okay, so using this we can model system. So we know using, so what is the first step? We already know some equations like Kirchhoff voltage law, Kirchhoff current law, and we know equations of the resistance V equal to IR, linear equations, the inductor, capacitor. So using those already existing elemental representation in the electrical domain, we write the differential equation. So we know the differential equation. So we'll try the differential equation of like dV. So we know input voltage V equal to I into R. This is the Kirchhoff law. We are applying laws, we already existing laws, plus what? L di by dt, L di by dt. This is the voltage across the inductor, L di by dt, plus voltage across the capacitor is I think 1 by C, 1 by C I dt, right? IR L di by dt 1 by C integral I dt. So we know this thing, we already know this models of this resistance, inductor, and capacitance. Okay, now in order to convert a differential equation model, we can differentiate again. I think we can differentiate again to make a differential equation model. Something if we differentiate, we'll differentiate the whole thing on the right hand side, right? So this is, we can write R into di by dt r into dy by dt plus L into d square I by dt square plus 1 by c integral. If we differentiate the integral, I can say it will become I by c, right? So we can write this equation dv by dt equal to dv by dt is nothing but this thing. So this is some this is a fast example. We know different elements of the system, and using the different elements, we applied some laws we already know. What are the laws? Kirchhoff law. We know there is capacitance equation, inductor equation, resistor equation. So we derived the equation of the system modeling or system parameters, right? Okay. Here I'm not specified what is my output. If I know what is my output, for example, if I have taken VC voltage across the capacitance as my output, I know this my output is dropped across this point, voltage across capacitance. Now I can draw the transfer function like output by input, and I get another differential equation. And if I get the Laplace transform of that, I'll get the transfer function. Okay, so I'm giving a small example. This is the right now what I have drawn. This is the first first example, first type of model, differential equation modeling. Okay, this is what my point. The different types of modeling. So the system, this is system given to you. This is system given to you. Now you have made the transfer function model of the system. Sorry, sorry, differential equation model of the system. Now if you are doing the transfer function modeling, how it looks like? Yeah, suppose VC is the output, or let's don't see VC as output. Let's take current. We are giving input voltage V, and we are getting a current, which is the response. So according to transfer function modeling, it will be like this. Say output by input, transfer function or Laplace transform of the current, Laplace transform of the voltage will be looking like this, something like this: 1 by R plus Ls plus 1 by Cs, something like this. Okay, so this is the second type, kind of mathematical or second kind of modeling, transfer function modeling. And how this equation came from? Where this equation came from? R plus Ls. This came from the differential equation we already written, right? We converted into Laplace transform, right? And we just do simplified. We put in the form input by output. Sorry, output by input, right? This is response. Here currently the response, voltage is I consider as input. So response by excitation. That means Is by Vs. It's nothing but this transfer function. So this is the second way of modeling for transfer function modeling, where we use the frequency domain in the Laplace domain transfer. Okay. Now, what is state space domain? How the state space domain look like? So in state space domain, we will be writing in a matrix kind of thing, a mathematical. Say, for example, we'll be representing the system like in a matrix representation. The system can be represented using state variables. Say, for example, the variables I can write here R by L, one first element 1 by L, and 1 by C, 0, 0, and this is multiplied by right IL inductor current, voltage across capacitance, something. So this is state space modeling. And this has to be plus with some other constants, like again another matrix 1 by L, constant 1 by L, 0. This is multiplied by V voltage. Right? So what we'll get? We'll get the output parameters. We'll get some another matrix with the rate of change of current, that is I dot. I'm just sending I dot and V voltage across something like this. Okay. So this is the way we are trying to model the system using state space modeling, right? So we have a lot of matrices, and we have a lot of state variables, and multiplying these variables, and at different points of time, we will get the output variable. So this is just understand for the time being. This is the way of modeling a system using state space modeling. Okay, fine. Now, how to start? What are the different ways? We already explained starting. There are two basic difference between analytical and experimental modeling. So right now we are focusing on analytical modeling because experimental modeling is very difficult, right? We cannot model a whole big system, pendulum or a train or aeroplane or a thing. Okay, so we using analytical modeling. So for, what are the different Let's see number of different steps before modeling a system. Now we have just seen overall view. Now we have to see what are the specific steps. The first step is we should know what we are trying to model. What we are trying to model this purpose. I'll just give an example after writing this. First, we should know what are the purpose of my modeling. What I'm trying to analyze. Is it efficiency or the speed or acceleration or is it something else? So we should know the purpose. Now then we should know the range, the boundaries. Define the boundaries. Define definition of boundaries. What does it mean by definition of boundaries? For example, we are taking example of this pendulum example. Pendulum example, you know how much this thing is going from which angle to which angle, right? This is your pendulum example. So you can give a range of the theta, right? This is theta, and we are talking pendulum. You know, this is theta. So this is the angle, maximum angle which you can spread. So we should have a range of this angle, or this much of this I'm expecting. This much is safe area. This is dangerous area, right? So all those things are different boundaries, and what are the maximum speed? What are the acceleration due to gravity, g, etc. So we have to define the uh, boundaries also. Then we have to start with the structure. We need to start with the structure, right? Then we have to propose or postulate a structure. Okay. Then we need to postulate a structure. Postulate structure. What is structure? We should know what are this components made of. For example, better we can know the electrical system. We can postulate a structure or a model of the electrical system. For example, transformer or a motor, or a generator, or a electronic system amplifier, right? So we can propose a model for that. Okay. So first step is uh, you should know what is the purpose. Second is you define boundaries. What are the range in which variable is going to act. Okay. Third is you to make a postulated structure. What kind of structure is it? Like mechanical model, mathematical representation of mechanical model, or electronic model, or electrical model. So you need to have structure. In last example, you have seen different model. Structure is consisting of resistance, inductance, capacitance, etc. Then from that structure, we should select variables. Select variables which are we are interested in. Select variables which you are interested in. Select variables of interest. Variables variables of interest. Okay, I already discussed there were a lot of variables, state variables, a lot of parameters within the system, but we are only interested in very specific parameters. For example, efficiency or the acceleration, velocity, etc., etc. So this is very important. Then from that we'll derive using the Kirchhoff law, Kirchhoff current law, we'll do mathematical equation, mathematical description. Mathematical description. Then we'll make the mathematical description of the system. Mathematical description of the system. How we do mathematical description? We use the mathematical description of each element. Each element we have to mathematically describe. Right? In last example, we have seen how to describe inductor, how we have described the capacitor with respect to voltage and current. So we have to describe each element of the structure in order to derive the mathematical description of the system. Now, once you know the differential equation of each element, now you need to apply the relevant physical laws. Apply relevant physical laws. Physical laws, which is relevant to Kirchhoff voltage law, Kirchhoff current law, right? Conservation of energy, first law of thermodynamics, second law of thermodynamics, etc. So once you know the individual mathematical distribution of the system, inductor, capacitor, inductor, resistance, then we need to apply the Kirchhoff voltage law, Kirchhoff current law, etc. We'll take an example. It will be more clear. Okay, then from this physical laws, if you apply physical laws and do some mathematical simplification, we'll get the final model. We'll get the final model. We get the final model, final mathematical model. Okay, now this model we can work on this model and we can analyze and validate and modify. Okay, so we'll get these are the different steps. Okay, for why we got the final model. Now we can analyze the system, analyze the system, we can test it, we can troubleshoot it, we can modify it also, right? So it's an important part of different design phase also if you have the model. Okay, so these are the different uses. So, I'll just try to recapitulate. So first we'll find define the purpose why we are trying to model system, what what are the industrial parameters, why we efficiency analysis, is the power analysis, or is the speed or safety, security, failure analysis, troubleshooting. So what is the purpose? Then we'll define boundaries, what are the variables and what are the limitations or scope of your variables, how much maximum you need to find, etc., etc. Then we are going to postulate a structure. You already know some previous background knowledge. So what this system may consist of, maybe resistant capacitor inductor, or maybe mechanical system, maybe damper, spring, etc. Then we select the variables of interest. Which are the variables we are interested in? Maybe voltage across capacitance, or maybe the acceleration due to gravity, or the efficiency. And then we write the mathematical description of each element. Very important. We are describing the mathematical description of each individual elements which we are interested in. Right? Then apply the overall physical laws like Kirchhoff voltage law, current law. Then we'll get a final equation. It's called the final model. Using this model, we can analyze the system, we will modify the system, we can troubleshoot the system, we can innovate something, we can see what kind of behavior it can happen, predict something, a anomaly, or we can, right? So this is things. Now we'll take an example each of these steps and we'll see. So we already take an example of a small electrical circuit. So before that, there are even if a electrical system we are taking, there can be different systems. First of all, physical systems can be different. Electrical systems can be mechanical system, and thermal systems. Your ACs, refrigerators also can be analyzed using as a thermal system. Hydraulic systems, right? The same thing which voltage for a which is driving a current can be analogous to the hydraulic system. We have a motor which is pressuring the fluid, right? Hydraulic. So these are the different systems which we will discuss as an system analogies, right? So when it comes to electrical system, when it comes to electrical systems, when it comes to electrical system, there are two kinds of modeling. One is voltage based. Voltage is voltage source. Voltage controlled circuits. Voltage control system. Why I'm defining, because we'll just take an example of the different steps in modeling. Voltage control modeling and current control modeling. Okay, we can just simply understand that we have two types of circuits. Some circuits we have voltage as a independent parameter, this controlling parameter. Some others as current as a controlling parameter. So other elements will be remaining the same. Other elements like resistance will be there in both. Resistance will be there in capacitance, and inductor will be there in both. Right, but in voltage control circuit, a voltage sourcing circuit, we have voltage will be the main important parameter, right? Voltage and charge. This is one voltage method. Voltage and charge is very important here. And but in current control or current source method, we have current is the most important parameter, which is using based on current, we'll write the equation, and flux. Flux, right? Basically, this is like representing using capacitance nature. We are focusing here. Which are the important variables? Q, charge in a capacitor, and voltage across a capacitor. But in inductive, we are just concerned about the current going through the inductor, the flux generated within inductor, right? Based on capacitance from inductor. Okay, so these are the two different way of modeling. So this is the, we can say, the we are trying to define the boundaries. What kind of modeling we are going to use? These are the individual elements. Okay, and we know all the mathematical representation of all this also. You know, V equal to IR, V equal to IR, and L, inductor with respect to voltage. What the equation of inductor with respect to voltage? We know V equal to L di by dt. Okay, so all this parameter with respect to the main voltage, we should know the equation. And capacitance, V equal to Q by C, right? Capacitance V equal to Q by C, Q by C, right? And charge with respect to voltage. Okay, that is with respect to this also fine. I think this also comes here. Q. Q equal to CV, something like that. Okay. And current also, the other equation will be same, R equal to IR, L, and so L with respect to current. Inductor with respect to current, we can say we can say I equal to, what is the equation of inductor? We can say this inductor, there is some inductor where the current is passing through it. This inductor where the current is passing through it. So this inductor value is L, right? So we know there is a flux generated within the inductor phi and phi, and we know the equation of phi equal to, equation of phi is directly proportional to the current, right? Phi is directly proportional to the current. So we can say phi equal to L into I. Okay, so we get phi equal to L into I. So we can say I equal to phi by L. And here I equal to V by R. And capacitance also we can write in terms of the current, I equal to C dV by dt, something like that. Okay, so each of this based on the element or based on the representation, we can write the same parameter in terms of its elemental nodes. Here in voltage control source we have voltage and charge. In current control we have current and flux, right? Now let's take an example how we apply this. Now we have made out the purpose of the model, the electrical system, input and output characteristics we should know, and we have defined the boundaries. And now we need to make a structure. For example, now the question is something. The question is like this: we have this circuit like this: a resistance, an inductor, and a capacitor. Okay, so this is a circuit. So this is problem you're given. You're given as circuit with all these parameters. So this is I, and this is we are getting a voltage V across this current source, right? So now I tried different currents. This is IR, IR. This is IL. This is IC. This is, let me write the parameters. This is the resistance, inductor, and capacitance. Okay, so we have the voltage across the current source or across each element, and we have the current passing through each element. Now, now we know the mathematical description of each of this element, resistance, inductor, and capacitance. Now we should know the according to our model. We have now first step. Purpose of the model has been defined, boundaries and structure has been defined. Now the variables of interest. So with the variables of interest, right now we have R, L, and C, and current passing through this R, L, and C, and voltage across them R, L, and C. Now we need to describe each element mathematically, which we just done. We are represented, each of this element using current and voltage equation. Right now we are here concerned about the current based equation. So we have now, so we can apply KCL now. Apply mathematical laws according to rule 6 or the step 6. We should apply relevant physical laws to the system. Now, what is relevant physical laws here? So I'm applying KCL, Kirchhoff current law, right? So this is a node. This is a node where different current is being sourced. So, so according to Kirchhoff current law, I know that I equal to I resistance plus I inductance plus I capacitance. So this is just application of some laws. Now this is nothing but I V by R plus IL, current across inductor is 1 by L integral V dt. Right? According to equations, we have already known that. And IC equal to capacitance, current across capacitance, IC into dV by dt. Right? Okay. Now there are two different ways which I have already discussed: voltage controlled sources, voltage controlled circuit representation, or current controlled resistance or current sourcing representation. So now we have to decide what kind of representation we want to use. In voltage control, we are representing voltage and Q, right? Based on Q, differential equation based on voltage and Q, charge. In current source, we will be representing using phi, flux, and I, current. So now we represent each of these things, convert each of these things into flux representation. Okay. So whatever we need the parameter, that is why we have to describe what kind of behavior we are trying to describe. Right here we are representing system in terms of flux and current. So now this is I. So how to represent I using the flux representation? Okay, I think you can go back to that equation from here. We have phi inductor equation, phi equal to Li, right? From this equation, you can derive all these variables with respect to phi. V, what is voltage across the inductor? L di by dt. So L di by dt becomes, in terms of phi, I becomes phi by L. So the basic thing is you represent each of those parameter in terms of phi and I. Then you'll get is in the current domain or current source representation. Right? So if I directly write theoretical point of view, we'll get I equal to 1 by R, 1 by R d phi by dt. You can try this with respect to 1 plus 1 by L into phi plus C into d square phi by dt square. I hope you can try this, right? You'll get try this. Now we can see in this equation we are representing using I and phi. So this is current source wave representation. I and phi. You can see every point in the mathematical representation have both flux, magnetic flux and current. So this is current controlled representation or current source representation. Right? The same system. Now the same system we can model using voltage representation. In voltage representation, we represent the system using voltage and charge. Right? In that case, the V will be V equal to, in terms of V. We'll get the equation in terms of V. V equal to, in terms of, instead of phi, we'll get in terms of Q. Here in terms of Q, we'll get in terms of Q. Okay. So I think we can try this. All those things starting from this thing. Phi equal to Li on the top right. Phi equal to Li, we can write phi in terms of all those things. For example, so for your kind representation, so for example, so we're starting from, there's an inductor, there's L, there's current to inductor. So flux is equal to inductance into current, right? Because we know phi flux is directly proportional to current. So phi equal to Li. This is the starting point of your representation. Now phi equal to Li. Now we know what is the voltage equation d phi by dt. Rate of change of flux is the voltage induced. So this is L di by dt. So we got voltage in terms of flux and L and I. So voltage is nothing but L di by dt, right? And now the current to the capacitor. This is in the inductor. Right? Now the current to the capacitor, we know 1 by C integral V dt. So the current to the capacitance. Nothing but I to the capacitance. So now we just need to substitute this. Now we should substitute this here. So what will be 1 by C d square I by dt square, something like it. This is voltage across the capacitor in terms of, right? So likewise, we can represent everything in terms of phi and I. Okay, and this is the first case, modeling using phi and I. Now let's see how to model using capacitance parameters like Q and V. Okay, so you can write the equation right now and try it, and you're getting now. You're drawing the same circuit, inductor and capacitor, right? So right now, if we model using the voltage, say now we are using voltage equation. So we know this is voltage across each of the element is same, right? Voltage across each of the element is same, so we can write like this also. So VR equal to VL equal to VC, and we can model like that, right? So the similar question can come, like we have input voltage V, and we have resistance, we have inductance and a capacitance, which we had discussed initially. So here we can represent voltage representation is better because we have resistance VR is the VL is the VC is also the. So we know the equation, Kirchhoff equations, VR plus VL plus VC, right? Now we can write all those parameters in terms of Q and V, right? So we can say I into R plus voltage equal inductance is L di by dt, di by dt plus voltage equals capacitance is equal to 1 by C into I dt. Now we are trying to convert everything in terms of charge because I and Q are related. Now this is nothing but R into dq by dt. This is nothing but current. Dq by dt is the current plus L into L into d square q by dt square in terms of q plus 1 by c. Integral I dt means q is already differential of current dq by dt. So integral of this means q into q. Okay, so here now we can see in this representation we are represented using voltage and q, v and q only. That means this is another way of representing using v and q, capacitance kind of representation. Voltage equals capacitance, charge equals capacitance. So last time we are representing phi and I, now we are representing v and q. Okay, so this is this mathematical description part, right? So once we have the mathematical description of each of this circuit element, capacitance, inductor, current, then we apply the law. What is physical law? Each model, right? So then we'll go the final model of the system or a circuit or a plant, right? So this just simplification. Now we should explain also the mathematical or the mechanical system, mechanical systems like um, pulley, gear in terms of mechanical counterparts. So I think I will not go into mechanical part because that is not much of practical for us. So we'll focus on the electrical part. Okay, so the first thing we discussed today was the transformer. So next class we may try to model the transformer. Okay, so the two things we try to model are transformer. Maybe transformer we can try to model next class using equations. So how those equations come from, where they are, from which laws they are coming from. We know already basics, transformer working, input voltage and output voltage as a ratio, which is decided by the number of turns of input and output, right? There's a core, there is a magnetic flux linked to it. So all those things will help us to make a model of the transistor, maybe mathematical, maybe circuit level, and from those individual parameters we derive the equations. We derive the equation using physical laws. So using those physical laws, we'll be able to get a model of a transformer. Now, in that model, instead of giving an input to the real transformer, troubleshooting the real transformer, we can give the input to the model, mathematical model or the circuit model of the transformer. And we can estimate the output. We can predict the output. We can predict what are the possible problems, what are the losses, why loss is more, why efficiency is less, etc. So this is basically today we have discussed few things. I'm just reviewing. There are basically two types of modeling. One is analytical modeling, and there is analytical modeling is the then mathematical or experimental. Sorry, analytical model is mathematical modeling, then experimental modeling. Right? Experimental modeling is difficult because we need to excite the system, the big system, right? Micro system, whatever. So it will be difficult. So we use analytical modeling. So why is modeling? Because helping, we'll get the mathematical representation of the plant and helps us in analysis and helps us in the see what are the variables are varying or evolution of system variables, right? Which decides the dynamics of the system, right? For example, temperature of a room, how it is changing, what rate it is changing, right? And what are the error, speed of a car is another example, and voltage current equations of a voltage and current values of a circuit is another example, right? So we have three types of modeling. One is differential equation modeling, transfer function modeling, state space modeling. These are coming under analytical modeling. So what is differential equation modeling? Using writing differential equation. This is time based, right? Based on time. Then transfer function modeling. This is applying Laplace transform on the differential equation, and this is a frequency domain representation. And last is the state space representation. This is the latest or modern control theory part. And in this we'll select a set of variables which describe the system behavior. Okay, that is state space modeling. Okay, and we are analyzing the system behavior in conjunction with this describe the system behavior with respect to state variables in conjunction with the input and output, right? Especially in first order representation we use for this thing and differential equation of state variables. So in your mind, it should be there that if the differential equation, dv by dt equal to r na di by dt by d square by d I by c, etc. That is the differential equation. And Laplace transform part or frequency domain representation, transfer function representation is is by vs equal to 1 divided by r plus ls plus 1 by cs, which you already studied last year or something. Now state space is based on matrices. A lot of matrices will be there, multiplication of matrix, some constants. That is state space mapping. That is ideally suited for computer simulations, etc. Should remember that. Right. Then we discuss what is the modeling purpose of modeling. Right. First, we will be focusing on purpose. Then we define the boundaries. What are the range of values we'll be getting? Then we'll postulate a structure, circuit, or then we'll select variables of interest. What is the variables of interest? I based on I and phi, flux or current, or voltage or charge, etc. Then we write the mathematical description of this model, each element. Then we apply physical laws like KVL, KCL, etc., etc. Then we got the final model. Now this model we can use it for analysis, troubleshooting, validation, and also modification and innovation, etc. Okay, so this much is next class we may try to see transformer model, and I think if you can brush up your Laplace transform. So while deriving transfer function model of some circuits, electrical circuits, we may require that thing. Okay, so mathematically we have discussed two types of physical parameters: voltage and charge based electrical modeling, which is nothing but voltage source modeling, voltage control modeling, and there is current and flux based current controller, current source modeling. So the same circuit, no, not same circuit, two different circuits we have model using current and voltage source. Okay, that's it. So if you have any doubts you can ask. If you have doubts you can ask, else you can put your roll number. So I not put the yeah, if any questions you can ask. Someone has raised your hand. Someone has raised their hand.